Stars, like all things in the universe, are born with a finite amount of fuel. Over time, they burn through this fuel, and eventually, they die. This is an immutable fact of the cosmos. Just as a car cannot run on water, stars cannot replenish their fuel once it's exhausted. Our own sun, for example, will one day burn out, marking the end of its life as a stable star. This process is inevitable, and any civilization with a basic understanding of astronomy and astrophysics will know that their star's time is limited. We humans appeared on Earth towards the latter part of the sun's stable period, inheriting a solar system that is far from perfect. Our sun is gradually increasing in brightness, a natural consequence of stellar physics. Over the next billion years or so, the sun will grow hotter, eventually baking the Earth and rendering it uninhabitable. The surface will become molten, and life as we know it will cease to exist. While there are potential ways to mitigate the sun's increasing fury, such as mining the outer layers of a red giant star for raw materials, the ultimate fate of the sun is sealed. It will become a stellar remnant, whether that's a cooling white dwarf, a neutron star, or a black hole. For smaller stars, the end might be a cooling blue dwarf. But no matter the path, all stars die. This raises a profound question. How can civilizations survive the trillions of years that lie ahead in the universe's future? The answer, it seems, lies in space travel. Not the kind of space travel we imagine today, exploring and colonizing new worlds, but space travel as a means of survival. For a civilization that lives millions or even billions of years, a journey of 10,000 years in a generational spacecraft might feel like a mere breath. The vastness of a single galaxy, or even travel to nearby galaxies at sublight speeds, becomes manageable when viewed through the lens of such immense timescales. To think like an alien or an advanced artificial intelligence requires us to move beyond human perspectives and time frames. For such entities, the colonization of all accessible stars might be a necessity, not a choice. Yet, even this strategy has its limits. In the far future, the universe itself will reach a point where no usable energy or resources remain. Black holes will evaporate, leaving behind cold, iron stars and cosmic cinders. At that point, any remaining civilizations will face the ultimate end, a time to turn out the lights and accept oblivion. But that future is trillions of years away. For now, the universe is still young, and its potential is vast. The death of stars and the rise of civilizations. The earliest stars in the universe were composed almost entirely of hydrogen and helium, the elements forged in the Big Bang. These stars lived fast and died young, exploding as supernovae and seeding the cosmos with heavier elements like carbon, oxygen, and iron. It was only after these first generations of stars that rocky planets, water, and life became possible. This means that we are not the first potential technological civilization in the universe. Far from it. In fact, we are likely early in the cosmic timeline. Our planet's 4.6 billion year history is only a fraction of the time that planets have existed in the universe. This leaves ample room for civilizations that arose billions of years before us, potentially reaching levels of technological advancement far beyond our imagination. It's entirely plausible that some of these civilizations have already faced the challenge of their stars dying and have developed strategies to survive. Stellar engines, moving stars to survive. One such strategy is the concept of a stellar engine, a megastructure designed to move an entire star system. The idea is rooted in the fact that stars are not stationary, they move through space. Over the course of a star's lifetime, it may pass close to other stars, offering opportunities for colonization without the need for long, perilous journeys across interstellar space. The most basic type of stellar engine is the Shkadov thruster, proposed by Dr. Leonid Shkadov in 1987. This concept involves building a massive mirror or statite near a star. The mirror reflects the star's radiation, creating an imbalance in the radiation pressure. This imbalance generates a net thrust, slowly pushing the star and its planets in a desired direction. While the thrust would be weak, it would be stable and require minimal maintenance over millions of years. There are other types of stellar engines as well. A Class B engine, for example, consists of two concentric spheres around a star. The inner sphere absorbs heat, while the outer sphere radiates it, creating a temperature difference that can be harnessed for energy. A Class C engine combines the propulsion of a Shkadov thruster with the energy production of a Class B engine, offering both mobility and power. More recent proposals include the Kaplan thruster, which uses a star's energy to excite a focused region of solar wind, creating directed plasma for propulsion. Another concept, the Svoronov star tug, is a hybrid design that increases efficiency and thrust power. These ideas, while still theoretical, demonstrate the potential for civilizations to manipulate their star systems on a grand scale. Binary stars and spider pulsars, a new frontier. A recent paper by Clement Vidal introduces an intriguing twist on the stellar engine concept, using binary star systems. About half of all stars in the Milky Way are part of binary or multiple star systems, and these systems could host advanced civilizations just as easily as single stars. Like our Sun Vital's idea focuses on a subclass of binary pulsars known as spider pulsars, which are actively destroying their companion stars. In a spider pulsar system, the pulsar bombards its companion star with intense radiation, stripping away its outer layers. This process creates a form of thrust that can be harnessed to move the entire star system. Unlike traditional stellar engines, spider pulsar engines are fully steerable, allowing for precise control over the system's motion. One candidate for such a system is the Black Widow pulsar PSR J1311-3430, which exhibits unusual behavior, including bursts of thrust in 3 equal sections of its orbital plane. Another candidate, PSR J1959+2048, shows an anomalous alignment with its motion through space, raising questions about whether it's being steered by an advanced civilization. The search for technosignatures. The concept of stellar engines opens up new possibilities for detecting technosignatures, evidence of advanced civilizations. If a civilization is using a spider pulsar engine to move its star system, we might be able to detect the resulting anomalies in the pulsar's behavior. This would represent a groundbreaking discovery, offering proof that we are not alone in the universe. However, the search for such technosignatures is still in its infancy. Many of the observed anomalies in spider pulsars could have natural explanations, and more data is needed to confirm their origins. Nevertheless, the idea of stellar engines challenges us to think creatively about how advanced civilizations might manipulate their environments and leave behind detectable traces. Conclusion: the future of cosmic survival. The death of stars is an inevitable part of the universe's life cycle, but it also presents a challenge for any civilization seeking to survive over cosmic timescales. Stellar engines, whether based on single stars or binary systems, offer a potential solution, a way to move entire star systems and extend the lifespan of a civilization. As we continue to explore the universe, we may one day discover evidence of such megastructures, revealing the presence of civilizations far more advanced than our own. Until then, the concept of stellar engines serves as a reminder of the boundless creativity and ingenuity that might exist among the stars.